Okay, so here is the sixth and last video for class number 2 in fluid mechanics. And we're going to talk about, class 2 is all about fluid properties. And this last fluid property is about surface tension and capillary action. So the main idea, I think, can be summarized as the difference between adhesion and cohesion. Let's see, I'm going to say this the wrong way. I'm going to double check. Adhesion is the attraction of different molecules to each other, whereas cohesion is the attraction of the same type of molecule to itself. And so the properties of fluids quite often can either be where something is sticky to other objects, or it could be sticky to itself. And one of the consequences, or one of the things about this property, is the formation of droplets and the formation of bubbles, right? Where a droplet is creating a surface because the water molecules are sticking to one another. If you get some air inside them, you can have now two surfaces, an outside surface and an inside surface. And soap will encourage this behavior. We'll often see this when it comes to a meniscus, right? Where you've seen especially when it's not a really small tube, but like, let's say, a test tube of water, you could see that the top of it, the top surface, forms a meniscus, where the water has a propensity to adhere and to the sides of the glass, especially if it's a clean glass, right? So it's important that it's not dirty. But if you have a clean glass, you could see that a meniscus forms. Where mercury, on the other hand, has much more self-stickiness to it. And it will have more cohesion than it has adhesion. So it'll have like a reversed meniscus in a similar type of tube. And we'll also see that there's something called capillary action, which is very much related to this. And a water will actually climb up a very thin tube. Whereas if you take a tube and you poke it down into the mercury, it'll actually go the opposite direction, right? But of course, these have to be really, really thin. And surface tension is, let's see, the surface tension itself has units of force per length, or pound per foot, or Newton per meter, and is the symbol sigma. So it looks a lot like stress, the same symbol that we use for stress, but it is not stress, it is the surface tension. And we'll switch over to our notes right here. So let's see, where we go. Boom, right there. And some instances where this plays a part, you could actually take a razor blade, and you could, if you place it down carefully, and don't cut yourself, it can float on the top. And that's kind of the combination of this surface tension of the skin, if you will, or a membrane at the surface. And you can see here's a water droplet that shows you some of the adhesion that takes place. This is the same property where like a water bug can walk on the surface of something. You can think of this as the strength of the membrane, and it's got a sigma. So one description of this process out here is non-displacement floating, right? Displacement usually, as we'll talk in classes coming up in fluid statics, displacement is usually, floating is usually to a quantity of displaced water or displaced liquid or whatever it is floating in. So we could actually have non-displacement floating based on this surface tension. And then the capillary action is something we just mentioned a second ago with this figure. So we have an equation for capillary action. The height that this thing will move up or go down is related to 2 times the surface tension, there's the sigma S, sometimes they leave that S off, divided by, and I think this is the, oh yeah, this is the specific weight, and divided by R, which is not the gas constant, it is the radius. For whatever reason, they're using capital R. It does not make a lot of sense. And it's times the cosine of this angle that's formed, and they're using theta here. I think in some books they use a phi instead right here. So here's, and this actually can be found from a free body diagram where you have like kind of H right here, right? So here's the weight of the of this piece, and right here is the force, but of course it's around the circumference. We're only seeing a cross section of it, and so from that we could solve for H, right? We take the sum of the forces here, and you'll see that because of that angle right here, that's where we get the cosine of theta. So it's like sort of the angle that's formed on the slope right there of the meniscus, or it could also be down that way right there if it's for this right here. So it's the FBD, and so that's all this is really solving for. So I have an example here. It's a quick example, and they say an open clean glass, right? So the glass being a clean tube gives us a theta equal to 0. So maybe I should have said that it has to be a clean glass. I guess maybe if it isn't a clean glass, they're saying that in this case the meniscus is, there isn't even a meniscus that's formed, right? Because of the clean glass too. I guess I have to assume that that's a true statement. Is vertically inserted into a pan of water. What tube diameter is needed if the water level in the tube is to rise to 1 tube diameter due to surface tension? Right. So I'll draw this pan of water here. I really recommend, you know, even if you don't feel comfortable with drawing things, that you still try to improve your sketching skills, because it really helps when you're looking at a problem that doesn't give you a diagram, or even if it does give you a diagram, to kind of sketch out what has taken place. And by doing so, you can kind of think your way through right here. So here is the H that we're looking for right here, and I've drawn it so it doesn't have a meniscus. I actually drew it with kind of waves on it for some reason. It's not the ocean, but I drew it that way. So we want to find out what this diameter is, right? The diameter of the tube should be the inside diameter, and so the equation we're using is the one from up above. H is equal to 2 sigma S divided by gamma R, cosine of that angle. Well, I used that symbol. It should be theta if we stick with what I just ran here. So we say we look up this for water in a we could, you know, here we're not really stuck with either US units or SI units. So let's go with SI, and I'm going to look this up. Let's see, am I going to get the same number? I don't know. Let's see if we get this number in SI for water. Sure, we get pretty close, right, to what I have, what I looked it up in the book. I looked it up in table 2.4 out of the book. Let's see. I'm not sure where else it's located in the book, but in table 2.4. I'll look it up in chapter 2. Really encourage you to get a hold of the book and let's take a look at it. Most exciting. Surface tension, table 2.4. Where'd you go? Table 2.4. There you go. So in table 2.4, if we can get this camera up over here, for water at 20 degrees Celsius, right? So they actually specific 0.073. Right? So 0.073. We'll get that back in there. All right, we'll put it back away. 0.073, and these are Newton per meter. Yeah. So plugging this back in. Okay, so we're going to have the H of this. We want to have is 2 as the diameter right there. So let's make it 2 times the radius, is what that needs to equal. And 2 times 0.073. And here is the cosine of 0 degrees, which is 1, right? And then we have the specific weight, which I had as 9810. That's newtons per cubic meter, right? And then we're going to solve for R. And if we solve for the radius of the thing, we get 2.728 e minus 3 meters. But we want, which turns out to a radius of 2.73 millimeters, excuse me. But we just want a diameter, so it's just going to be 2 times that, or 5.46 millimeters. And you can kind of picture that a little bit better by taking a look at our handy dandy ruler right here and kind of seeing how big that is. All right, so that's like about, right here, here's 1 centimeter, so it's somewhere here, and then about 5 millimeters, like right in there. 5.5 millimeters is how big that tube would have to be for it to rise up that same height and form kind of a square going on right there. So that's it for class number 2. It was a lot of videos. Thank you for watching, if you did.